Okay, I want to discuss orthogonal sets of vectors, sets of orthogonal vectors, orthonormal sets, and orthogonal matrices. Okay, let's go ahead and talk just a little bit about our first definition here. A set of vectors, u1 through un, are orthogonal or form an orthogonal set if they are non-zero. Okay, you can't have any zero ones in here, but if I take the dot product of two distinct ones, I always end up getting 0. Okay, so ui dotted with uj is 0 whenever I is different than j. Okay, and that's supposed to hold for all I and j. What's an example of an orthogonal set would be our regular ijk system in R cubed. Okay, you can see that if I take the dot product of any two distinct ones here, I end up getting what? 0. Okay, there's other examples, obviously. If this was all there was, it may not be so interesting. Okay, I've got three vectors here: 1, -1, 1, 3, 1, -2, and 1, 5, 4, and I claim these are also an orthogonal set in R cubed. Okay, here if I take the dot product of any two of them, take them two at a time, two distinct ones I mean, and take their dot products, I get 0 every single time, as you can see and easily verify. Okay, so this is an orthogonal set. Alrighty. Sorry, I was a little sloppy on this one, but I hope you can read it. A set of vectors is orthonormal. Okay, that's supposed to be an N. A set of vectors is orthonormal if the set of vectors is orthogonal. Okay, so it satisfies this. And each vector in the set has magnitude 1. In other words, each of the vectors is actually a unit vector. Okay, now let's go back and think for a second here. ijk, that's an orthonormal set. Okay, we saw that they're orthogonal, and notice that the magnitude of each one of these is actually equal to 1. So that's what we would call the standard basis for R cubed, and that is an orthonormal set. Okay. Okay. Let's come back here. I have another example here. 1 over the square root of 3, -1 over the square root of 3, 1 over the square root of 3, 3 over the square root of 14, 1 over the square root of 14, -2 over the square root of 14, 1 over the square root of 42, 5 over the square root of 42, and 4 over the square root of 42 is an orthonormal set, I claim. Where did I get this one? Well, I took this set of orthogonal vectors, and what I did was normalize, quote unquote, each of the vectors. Okay? In other words, I just took each of those vectors, right, and divided by their own magnitudes, making them what? Unit vectors. Okay? Can you see, as an exercise for you, that if I have, let's say for example, a set of vectors that is orthogonal, if I multiply those vectors by what? A non-zero constant, you know, a different one in each case maybe, the set is still orthogonal. Okay, this will still be satisfied. So I could multiply by arbitrary non-zero constants here, or divide by arbitrary non-zero constants through these, and I still have an orthogonal set. So that means, since this was orthogonal, and I'm just dividing each one by its own magnitude, these are still orthogonal. Okay, so you could try that. Their dot products are still going to be 0 if I take them two at a time here. But they're all now unit vectors because I divided each of those vectors by their own magnitude. Okay, so if you've got an orthogonal set, you can always produce from it what? An orthonormal set by just taking those vectors and dividing each of those vectors by their own magnitudes. Okay, ready? Hope that made sense. Okay, some things we do with these. Suppose V is a vector space, and U1, U2 through UK is an orthogonal basis for V. Okay, I just used a different subscript, K instead of N. Okay, usually we use N or M. I'm going to use K this time for no particular reason. Okay, if V is a vector in cap V, right, so V bar there is just a vector somewhere in this vector space, then since this is an orthogonal basis, okay, first of all, it's a basis, so that means it has what? A unique expression as a linear combination of vectors from this set here. Okay, so that's clear. A1, U1, A2, U2, and so on, down to AK, UK. Okay, so that's unique. Okay, and I can actually, what? Compute the value of each of these A's, right, those scalars, in the following way, I claim. Here's the idea. I claim A sub I is V, whatever this vector is, dotted with U sub I divided by U sub I dotted with U sub I. Okay? And you can see that very simply by just doing what? Let's say I want A1 here. Okay? If I want A1, find out what that scalar is. Just dot both sides of this equation by U sub 1. Okay? Now we know that the dot product has the nice distributive property here. So when I dot with U1, it would dot here and so forth. And we also have the associative scalar property. A1 times U1 dotted with U1. Well, U1 divided by dotted with U1 is whatever. Okay? Okay? But I would get what for all these other ones when I dot them? 0, 0, 0, 0, 0, 0, right? Because they're what? Orthogonal. This is an orthogonal set. So if I dot any two different ones from this set, I get 0 here. And anyways, then isolating, for example, A sub 1, I would just go V dot U1 divided by U1 dotted with U1. Okay, and this is the general case where you end up dotting on both sides by U sub I. Okay, so I hope you followed that. Okay, so it's easy to, we've got a formula for these scalars this time. Okay, by the way, if I take this and stick it back in the formula here I wrote it with our convenient summation notation. This is what it would actually look like. V is the summation I goes from 1 to K. Okay, V dot U sub I dotted U sub I times what? That's a scalar in parentheses times U sub I or U sub I bar. Okay, do you recognize this expression right there? You should from the previous chapter, right? That is what? That's the projection onto U sub I of the vector V. Okay, so V is actually this. Maybe I'll write it again here. Okay, this is sometimes called a Fourier expansion of V. Okay, a Fourier expansion in terms of an orthogonal basis. Okay, so there it is. In the case that the basis is orthonormal, the Fourier expansion takes a particularly easy form. Well, if this is orthonormal, that means what? The magnitude of each one of these is actually equal to 1. Now, in our formula, I'm going U sub I dotted U sub I in the denominator. U sub I dotted with U sub I is the square of the magnitude of U sub I. But if the magnitude of each of these U sub i's is what? 1, I'm squaring 1 in the denominator, so all I'm left with is the numerator. So we'd have the particularly easy form written this way. The summation V equals the summation I goes from 1 to K. V dotted with U sub I U sub I hat. Remember, if I put hats on vectors, this is very physics. That means they're what? Unit vectors. Okay? Alrighty. So those are unit vectors. Let's take an example here. I keep writing Fourier series. That's a concept in, well, usually used in differential equations. Okay, but the Fourier expansion of this particular vector in 3 space, let's go 2, 11, negative 10. And then I've got, this is our old friend here that I took from the second example, the first non-trivial example. We've got this basis, 1, negative 1, 1, 3, 1, negative 2, 1, 5, 4. Okay, let's go ahead and find its Fourier expansion. So what I'm going to do is what? I'm going to find A1. I dot this between this vector V and the first vector, which I'm calling V sub 1 or U sub 1, or U sub 1, I guess I'm calling it. All right, take the dot product up there. This is sometimes called scalar projection, by the way. Okay, take the dot product over there divided by what? The square of the magnitude underneath. And I get negative 19/3. And I do that with the second vector. And then I do that with the third vector. Okay, so just following the formula here. That's all we're doing. Okay, following this formula. Okay, and then we've got this Fourier expansion. Okay, so there you go. Okay, these numbers are sometimes called scalar projection. Okay, so that's the idea. Okay, so finding the scalars in the basis expansion is particularly easy in the case of orthogonal bases, or even better, orthonormal bases. Okay? Let's go on here. Let's talk about something else. A real n by n matrix U is called orthogonal if U times U transpose is the same as U transpose times U is what? I sub n. Maybe I should use I sub n as the n by n identity. Another way of saying this is simply this, that U inverse is equal to U transpose. Okay, U inverse is equal to U transpose. Because this U is a square matrix, well, I make that comment down here. Okay, oh wait, before I go on here, when we get to complex n by n matrices, it'll be orthogonal. We've got to come up with something called the conjugate transpose instead of just the transpose. Okay, but that's in the future. You don't have to worry about it right now. Right now, we're just going to be worried about real n by n matrices. Let's take a quick example. Okay, I've got 1 over the square root of 5, 2 over the square root of 5, 2 over the square root of 5, negative 1 over the square root of 5, and I claim this is a 2 by 2 orthogonal matrix. Okay, I'm just going to take the matrix and multiply it by its transpose in either order. We're going to show that here in a second. I'm going to mention this right now. Doesn't matter what order we actually take this product in. If you're testing for orthogonality on a square matrix, a real square matrix, all you have to do is multiply it one way or the other, and if you end up with the appropriate identity matrix, multiplicative identity of the correct magnitude or correct dimensions, then you're in good shape. You don't have to test it the other way. Okay, and I throw that in here. And I just went through the calculation, and I indeed got 1001. Remember that if A is an n by n matrix and A times B is the identity, okay, n by n identity, for some n by n matrix B, then B is actually A inverse, right? Okay, and you remember we showed that A inverse equals A inverse A is the identity. So in other words, if you got this satisfied just one direction, then it actually works both directions on square matrices. Okay, so that would mean BA equals I sub n also. Applying this to the orthogonal matrices, it follows that it's sufficient to show then either U transposes I or vice versa. Okay, just to prove that it's orthogonal. Okay? Okay, so we're almost done here. We just got one more page. The orthonormal basis, the rows of an n, here's something to remember, the rows of an n by n orthogonal matrix form an orthonormal basis for Rn. Okay, these are actually what, row vectors here. Any orthonormal basis of Rn can be used to construct an n by n orthogonal matrix. So there's a close tie-in between what, orthonormal sets of orthonormal vectors and what, orthonormal bases or orthonormal matrices. Okay, and we're going to see that here. By the way, a better name for orthogonal matrix probably would have been an orthonormal matrix, but history hasn't been kind to us. People would argue this is and you'll see why, this is a better word, should be orthonormal matrix. Okay. Well, anyways, let's get to it. Okay. Now, let's go ahead and say I've got some row vectors. U1, do you remember my notation where I put the bar underneath? That means a row vector. That's just my personal notation. Not everybody does that. In fact, I don't know anybody else that does. But anyway, okay, so these are what? Row vectors. Okay, so, 1 by n vectors. U transpose would be what? Notice how the bars have moved up top. Okay, so these would get switched around here. So this would be what? An n by n matrix where these are now what? Column vectors, right? The bar is moved on top. That's just the transpose of U1 This is the transpose of un. Anyway, okay? Now, well, I'm going to go ahead and multiply these two matrices, okay? Just point something out here. If I multiply these two matrices, again, it's not going to matter what order I ultimately do this, but one's far more convenient for my argument. This way is more convenient for my argument here. Anyways, when I multiply the two matrices here, I want you to think about this, okay? This would end up multiplying on each of these row vectors. This column vector would multiply on each of these row vectors. That turns out to be exactly the same thing as the dot product of the column vectors like this. U1 dotted with U1, U2 dotted with U2. Notice the bars on top, UN dotted with U1. Okay, then when I multiply with the second column on each of these, I get U1 dotted with U2, U2 dotted with U2, UN dotted with UN, and so forth, all the way to the very end. Now remember, this is supposed to be what? This is supposed to be an orthogonal matrix, this fellow, okay? So if I take the product of these two, I should be getting what? The n by n identity. That means I'm getting what? 1 down the main diagonal, all ones, and zeros everywhere else. But when you examine that, right here, that means that you could see I get what? 1 in each of these cases. Every matrix dotted, or I should say every vector dotted with itself as a column or as a row is what? Is 1, but if I dot two distinct ones, I get 0, right, in order to get the n by n identity. That means what? These forms an orthonormal set, okay? That forms an orthonormal set then, by definition here. Okay, notice then that's, you know, like we said, that would be a better word, orthonormal here. Anyway, and I claim an orthonormal set in Rn, a set of n vectors, okay, in Rn, okay, actually forms a basis. All right, here's an exercise for you. This is because they're what? Linearly independent, okay? The same holds for the rows, if you'd rather think of it with columns or rows. By the way, up here I could say rows instead of columns, okay, or columns instead of rows, okay? But you want to show that these are linearly independent. Okay, can you do that? I'll give you a hint. Think of Fourier series, okay? Excuse me, Fourier expansions, okay? Remember the linearly independent set of n vectors and must span R n. Looks like a 5. Why did I put 5 there? Hence, the rows or columns serve as a basis for R1 by n, or respectively Rn by 1. Okay, for a given orthonormal basis for Rn, okay, either as rows or columns, the construction in the proof above will create an orthogonal matrix. I almost said orthonormal matrix, which is what it should be, okay, by just doing this. So, in other words, you can turn this around. If you've got a bunch of orthogonal vectors, you can form an orthonormal set of vectors. You can form an orthogonal matrix very easily just by writing them either as columns or rows, whichever way you want, and you've got it. Okay, here's a couple propositions that are easy exercises for you. Okay, try these. U is an orthogonal matrix, then I claim its determinant is plus or minus 1. That's an exercise for you. Okay, and let's say we've got a fixed n. The set of all n by n orthogonal matrices is closed under matrix multiplication. You know what that means. So that means the product of any two n by n orthogonal matrices is also an n by n orthogonal matrix. Prove that. It's closed under inverses. So in other words, the inverse of an n by n orthogonal matrix is an n by n orthogonal matrix. It also contains I sub n, the identity. These are exercises for you. Okay. By the way, in the parlance of mathematics here, the way we would say this, we would say this proposition says that the n by n orthogonal matrices form a multiplicative group, a type of algebraic structure. Okay, well, you should be able to do those problems I've assigned now. Hopefully this will help out. I'll have another video quite soon.